Okay, welcome to the talk. It's kind of a tech talk on Lego Mosaics, techniques and algorithms. Let's just get into it. We have a table of contents. We have some time for Q&A at the end, but of course, if you want, of course, if you want to interrupt me during it, you can ask questions as well. I think this is meant to end at like 1:50, so we'll try to leave around 10 minutes at the end for Q&A. If you have other questions, you can also grab my contact info at the end and you can just email me or something. Yeah, so this is table of contents. Sounds fun. Okay, intro, who am I? My name is Dave. I'm a software engineer by day and Lego person by night, or whatever we're calling it now. I graduated from Georgia Tech in 2019 with a computer science degree, and I specialized in intelligence and theory. And this talk is going to be, mostly about how you can take that knowledge and apply it to Lego, right? So who is this presentation for? You don't need a degree in computer science. You don't need like a massive understanding of computer science or even math in order to benefit from this. I think it's like really cool stuff. And like, even if you're not interested in ever coding anything that does this sort of stuff, it's still really important. It's still really cool to know this sort of stuff because it can improve the way that you actually approach making your own Lego mosaics. Disclaimer, so this work isn't related to my normal job. All of the code is publicly available. Not all concepts here have publicly available code. Even if I have coded some stuff that's, in some of these slides, I haven't put every single thing online, mainly because the code is really janky and embarrassing. All right, sweet. So what is a Lego mosaic? Lego mosaics are, of course, just 2D images. I say 2D, we'll get to that later, that are built using Lego bricks. So you take, you of course know this, right? There's a big backing plate and then you put individual pixels, individual pieces in order to make a Lego mosaic. Lego mosaics have been around for decades. So there have actually been some very, very early Lego sets that are actually mosaic style Lego sets. It's been around for a while and it's like been really, really popular within the adult Lego community as well. Where we actually come in is in 2020. So in 2020, at least I think it was 2020, Lego released the Lego art theme. So this was aimed towards adults and it was more lifestyle style mosaics in terms of like, hey, we want this to be like a big fancy, like more quote unquote serious thing. And this is also where I came into looking at Lego mosaics and writing software for Lego mosaics. Speaking of software for Lego mosaics, this has also existed for a while. There's a thing at some Lego stores where you can go in, you can take a picture of yourself and it generates a mosaic. It's like a black and white mosaic. I guess they put it online as well very, very recently. So some of the Lego mosaic software has been created by Lego themselves. And other Lego mosaic software has existed for quite a long time, like for varying platforms and stuff like that with varying capabilities. And I think the most important thing that we need to keep in mind when we talk about Lego mosaic software is Lego mosaic software it should be designed to assist humans rather than replace humans. At the end of the day, the human is going to decide what picture to make. And at the end of the day, humans are going to be the ones actually looking at these pictures. So what we're going to explore today is how such software is developed. So the first few slides are basically going to be like the basics of like how most Lego mosaic software works. And then past that, we're going to go into the advanced stuff and stuff that's only really been explored in software in the past year or so. The example software that I've given over here takes an image and basically converts it into a Lego mosaic using existing, available Lego pieces. This is a piece of software that I wrote called Lego Art Remix. It's completely open source, so you can grab the source code at the end and look through it if you want. It's free to use. I'll talk a little bit about that at the end. What I won't speak about. So when it comes to software, there is a lot more stuff that I could go into, but this is probably not an audience that would be interested in it. I can go over this briefly, but unless you have a software engineering background, you probably won't be really interested in this stuff. So stuff like project architecture, deployment, security, performance optimizations. Performance optimizations are really important because working with image files, it can get very expensive very quickly, not just in terms of time, but also in terms of RAM. Memory management, RAM, HTML canvas usage, some fancy API that exists, and HTML, blah, blah, blah. Interactive pixel editing, how you can make an interactive experience. PDF generation, how you can generate instructions. Neural network deployment plus details. So we'll be talking a little bit about when it's appropriate to use neural networks in order to assist this type of software, and other software engineering stuff. This stuff is kind of, I mean, I said it's kind of abstract right now, but when you're actually deploying this software, it becomes very, very important, because whenever you're working with images and software, you need to be very, very careful about, like, you know, what you send over the network, how much RAM the client has, that sort of stuff. We won't talk about that. If you're interested, you can look at the Lego Art Remix code, or you can reach out to me. Okay, don't panic. If you don't understand some of the details of the math, some of the slides are gonna have math. It's gonna look a little fancy, but just focus on the idea of what the math is trying to capture, right? Like, don't focus on the details if you don't want to. Because, you know, it's a little bit of a pain. Okay, sweet. Any questions so far? Okay, sweet. Let's get into it. Okay, so the first concept we're going to cover is color distance. What is color? It's a very interesting question, right? On the most basic level, color is just different wavelengths of light. Growing up, as school children, we were told that color is made up of the three primary colors, red, blue, and yellow. But in terms of what color actually is, it's actually a much more abstract question in terms of like the spectrum of color, brightness of color, because we are not interested necessarily in what the color is from a nature point of view. As humans, we are more interested in how we interpret color. And that's where things get really, really interesting, right? So we're talking about software. So how do computers represent color, right? So the most common representation of color in computers is RGB. Hex codes are another different way to look at them. They're just a different, you know, storage format. And then we get to the concept of color distance. And the color distance concept is a really important concept when you get to Lego Mosaics, because this is what we're going to build our algorithms on top of, right? So I'm so happy that the slide's actually showing in the correct colors, because this would be really difficult if it wasn't. Okay, so you see color distance, pink and purple. So that's a function that takes in two colors and just returns a number that is some sort of distance, some sort of measure of how different these two colors are, right? So pink and purple, if you have a reasonable color distance function, then the color distance between pink and purple is less than the color distance between pink and green, because pink and green are very different colors, right? At least according to the human eye, right? So when you come into color spaces, a very natural way to code this is convert the color to RGB in the computer, right? Choose 2 points in 3D space where RG and B are the coordinates in 3D space. And then the color distance is just the Euclidean distance between them, right? So that's very, very cheap for a computer to calculate. And it's the most natural thing that like a human mind would think of. What's interesting is that even though this is the most mathematically clean you can get, mostly the most mathematically clean you can get, there are actually some way more sophisticated color functions that have been in development for, decades, which are meant to more closely approximate what the human eye sees, right? RG, if you're ever like trying to make a Lego Mosaic software, whatever, RGB is a great place to start. But later you probably want to swap it out with some of the other functions and just use a library or something, right? Okay, mosaic creation. Now that we have the concept of color distance, it's actually very, very easy to get to our quote unquote first version of a Lego Mosaic software. All right, so what do? We can view Lego Mosaic creation as minimizing color distance, right? So let's say I have a 48 by 48 image, right? I'll have an example right after this slide, but I have a 48 by 48 image. I have it as an image file and I want to convert it to a Lego Mosaic. Here's what I do. I take the picture. For every pixel in the picture, I get the RGB color or like HSV color or whatever the hell I want to do. And I find the closest associated Lego color according to the color distance function I've defined, right? So basically you scale it down to the resolution you want. For every pixel, find the closest Lego color, right? That's the most natural thing to do, right? And that's something that a computer can do many, many times faster than a human can do. And mathematically, if you want to get technical about it, we are minimizing this sigma. So all this means is summing over every pixel position. So if you have every row and column is like I and j, for every pixel, minimize the color distance to the whatever replacement Lego color you have, and your final image will actually minimize the sum of those distances, right? So our algorithm minimizes sigma color dist I to j, sigma from I to j of color distance between the original and the replacement pixels, right? Any questions so far? The light is actually shining like kind of in my eyes. So just like say something, because if you raise your hand, I might not be able to see it. I'm kind of blind right now. Oh yeah, sweet. So let's look at some examples. And this is something that's very, very easy to code actually. So you have like the input logo of a certain company, and then you scale it down to 48 by 48. And then for every single pixel, find the closest associated Lego color. Right, easy. And the beauty of this approach is that it literally it's designed so it can like any type of image can be captured by this, right? You just lose some detail, right? So this is like a kind of like a simpler picture, and then you get to a more complex picture, which is the 2010s hit album Speak Now by Taylor Swift. This album slaps. Have you heard this album? I am not, okay. So you scale it down and then you take the same approach. Essentially the same thing happens, we're just losing detail, right? Okay, easy peasy, right? Now things get a little complicated in terms of when Lego actually released their Lego art line, they actually had a press release, or it might have been in the instructions where they spoke about how they were trying to get art that was more aesthetically pleasing, quote unquote, because you know all art is subjective, I guess, right? And what they realized was images generally look smoother if instead of using square pixels, you use round pixels. Okay, sweet. So now we're using round pixels with a black background. And when this actually happened, a lot of Lego Mosaic software kind of, for lack of a better word, like doesn't work that well in terms of if you code it in the way that I described earlier, then you usually get a much darker image. Why is this? Because you have a black background, and if you have a round pixel, a lot of the background bleeds through. There's actually a really, really simple fix for this. All you need to do is before you align the color, you just use math again, right? So if you remember geometry, right? You have a circle within a square, and the proportion of the circle within the square is pi by 4, right? So you need to multiply the brightness by pi by 4 because everything else is just completely black. Okay, right? So that's one complication dealt with. Sorry? Yeah. So the software can do that. Yeah. There's like a little setting over there. There's a checkbox. Okay. Transparency. Transparency is incredibly interesting, right? So Lego, when we usually think of Lego art, we don't really consider transparency. But there's actually some really cool possibilities when you use transparency, like you can put light filtering through the back. That's pretty cool. Turns out that certain image formats, such as PNGs, encode transparency information. For every pixel in the image, it also, in addition to the R, G, and B, it has like a fourth value that tells you how transparent said pixel is. So now we come to the question of how can we account for that in our software, right? Now, the interesting thing about Lego studs is that if, like, let's say you have the original image, which is some shade of red that's quite transparent. Now we are in this weird situation where we're like, do you choose the normal red or do you choose the transparent red? I say red, there might be all, different shades of red, which is kind of annoying. So what we do is we can actually account for this by adding a transparency factor to the original color distance. Now, basically, when we're doing the color distance calculation between the original pixel and the new pixel, the original pixel and the replacement Lego color, what we do is we do the normal color distance function without transparency, and then we add in a transparency factor. Without transparency is much, much easier to do because not a lot of color distance functions actually account for transparency particularly well. And then we have a transparency factor where if you're, depending on how close you are in transparency to the original color, the factor will be like lower or higher, right? So the closer the original is to the replacement in transparency, if both of them are very transparent or both of them are very opaque, then the transparency factor will be lower. And this simple replacement is literally a drag and drop replacement into the code. And you can account for that pretty easily. Don't forget to change the backing plate though, because this is completely useless if the back is still black. Like, what are you doing? Oh yeah. Next up is metallicity. So transparency and let me just check the time. Transparency and metallicity are very similar concepts on the surface, but it's a massive pain because you can't actually get metallicity of an image really easily in terms of the input format. So what you do is, you can use a neural network on the original image. There are lots of models that exist for this, and neural networks tend to do this sort of texture detection very well, where basically they can identify how confident it is that the original pixel is meant to represent a metal. So we can use the same trick. Okay, last thing I'll briefly touch upon is complex pixels. So far, we've been talking about pixels in terms of 1x1s, but sometimes pixels aren't points. In terms of you have asymmetrical pixels, like the Lego dots, same as pixel pieces with prints, multi-pixel pieces, such as like that 2x4 plate. I'm actually going to talk about that a little later in terms of efficient tiling algorithms, and raised pixels, which we'll get to when we speak about 3D mosaics. Next up is price optimization. Lego is hella expensive. So when you actually are making an image, the question is, okay, I have the original color, which is sort of like a maroon, and I need to buy either dark red or normal red. And dark red is much more expensive than normal red, and it's actually closer, right? So I think the question we need to ask ourselves is like, how close is close enough to warrant the price change? And how can we do this efficiently? Because now instead of optimizing for for one function, we're optimizing for two functions. It turns out that we can fold that back into one function. We can use the transparency trick again, where basically we do color distance, original, comma, replacement, plus k times the price of the replacement, right? So basically, the higher k is, the more we care about the price, right? So the higher the cost is, the further we are from the original in terms of like, you're good, but you're also expensive, right? And this is very, very efficient. This is very efficient to code. The actual pain to code is actually reliably finding the prices. Okay, dithering, I'm not going to talk about this too much, but you can look it up later. I have a reference over there. It's a concept that you actually want to look at when you're looking at very, very large mosaics with limited color spaces. It's not super interesting for most people because like the mosaic needs to get very large for this to be useful, but it's kind of cool to look into. Next up, we have the remix problem. So the remix problem is something that, as far as I'm aware, didn't show up much before the year 2020. So what if we have limited number of studs for each color? Instead of every pixel, I'll say I have unlimited blue. What if I have a limited amount of blue, a limited amount of white, a limited amount of red, and all the color counts are different, right? I have the same goal, which is to minimize the sigma of the color distances, but I have different constraints. And what turns from a very, very easy problem that like you can finish coding an app for in like a couple of hours becomes something that's like nightmarishly difficult to actually figure out. So this is much harder to minimize now. So for example, you see this, this mosaic, right? This example, the input mosaic is, of course, like the Iron Man Lego mosaic, if anybody is, I guess you're probably familiar with that. And then we have the picture that we want to actually make is the hit 2016 album, It Doesn't Have to Make Sense by Ingrid Michaelson. Has anyone heard that? Yo, this album also slaps, you should listen to it. Oh yeah, but look at the picture. The picture doesn't look anything like Iron Man, but we're going to design an algorithm that can actually convert Iron Man into this pretty easily. It sounds like dark magic, but it's actually possible to do. Okay, so why do you care? Why do people care? You want to design something with your existing pieces without having to buy more pieces. You want to design a mock from an existing set so you can share it to other people, right? I think like a really cool thing about Lego art as a theme is that now it's taken the idea of Lego mosaics from something that's niche to something that's like very widely accessible. Right? And because you want to design something that's easy to acquire, you think it would be cool, right? You know, oh, cool, Iron Man turns into this. It sounds completely whack, but it's cool. And then the final one is you work for Lego. So Lego put out a Harry Potter set. And then like a couple of months later, they were like, oh crap, we can put out more instructions for the same set. And they literally like posted this. I don't know if they used my app, but like if they did, it'll make me feel good. Also, if you work for Lego, hi, you should use the app. Oh yeah. This is where things get a little nasty. So it turns out that we actually need to, we'll take a short detour into something more computer sciencey, which is the assignment problem. When I say problem, it's like a math problem or a computer science problem. The assignment problem has been around for decades. And the idea of the assignment problem is we have a number of agents and a number of tasks, and we need to assign tasks to agents in order to minimize or maximize some cost function. And a lot of algorithms exist for the assignment problem. And the assignment problem reduces to linear programming. Now, when I say reduces to, I mean, if we have an algorithm that can solve linear programming, we have an algorithm that we can use that algorithm to solve the assignment problem. And now you're wondering what the hell is linear programming. Linear programming is another problem that's decades old, and it has a lot of good solutions. It has a lot of powerful libraries that it can actually solve it. It's a well-known problem in computer science. Or is anybody here, if you're in business or economics, you would probably know. Has anybody heard of the linear programming problem? Yeah, I see some people. Yeah. So this is usually used to optimize like trade routes and stuff like that. But it can also be used to solve the assignment problem. Why do we care? Because the remix problem also reduces to the assignment problem, right? So if we have a solution to linear programming, we can use it to solve the assignment problem, and we can use it to solve the remix problem, right? So remix problem reduces to the assignment problem in polynomial time. That means we don't have to do any like crazy cost sacrifices in order to actually reduce the problem, right? Instead of agents and tasks, we have studs and pixels, right? So we have original colors and replacement colors. And the assignment problem similarly reduces to linear programming. Many libraries exist to solve linear programs, right? Where you have a bunch of your variables and constraints, right? Easy peasy, we've done it, right? No, not quite. The catch, it's slow and memory usage can be bad, right? When I say it's slow, I mean, we are literally dealing with thousands of pixels, right? And on many machines, that's not feasible to solve very quickly, which is kind of annoying, right? You can get around this by reducing the problem size by like trying to merge pixels, trying to merge regions and stuff, but that's not very reliable and it can fall apart very quickly. Any questions? Okay, so what do? We write an algorithm to solve the linear program, to solve the remix problem faster. When we say we want to solve the remix problem faster, we say it's okay if we don't get the optimal solution according to math, but what we'll do is we'll run a fast approximation algorithm. I've described it here. It's a two-phase approximation algorithm where we do some, I'll describe it like really briefly, where we basically do some greedy matching and then we figure out what the problematic pixels are, and then we do some more greedy matching. It's not perfect, but in practice, it works very, very well. And the reasons it works well are very, very interesting, right? So it's, in most cases, if the user has at least like, let's say, if the closest color was white, then it's reasonable to assume that the user has a bunch of white studs or are able to acquire more. So this two-phase approach actually allows us to very, very easily, quote unquote, fix bad images, right? So we take our earlier example, the hit 2010 album, Speak Now by Taylor Swift, right? And we try to make this using the Iron Man mosaic, right? This is literally the same algorithm where we actually tried to make it, and where it would take like hours and hours for us to figure out. This conversion ran in less than a second on like my phone, right? And the good thing about the two-phase approach is it's very easy to see what the problem is, right? We have a bunch of missing white pieces and the algorithm was like, ah, crap, I don't have anything for this. Yeah, I guess we still have blue. Yeah, just chuck that in, right? But because of this approach, we actually know that the only missing thing, that the biggest missing thing is a bunch of white pixels. So we can just chuck in like around 1,000 other white stars and it gets us very, very close to the original image, which is really, really cool, especially because of how fast this runs.
Can you, before you go on that slide, the middle image had a lot of tan on the skin tone, and then the final image did not.
So that's also turned into white, because it turns out that a side effect of adding in the background, it also changes skin tone. I didn't notice that.
Yeah, because I mean, the tan looks better from far away.
Okay, so it looks better from far away, right? But mathematically, when it comes to color distance, according to the color distance function, this is better, right? But then that's also comes into the subjectivity of the human eye, right? Maybe we didn't choose the right color distance function.
Another question too, actually.
Yeah.
Is it possible to prioritize like interesting parts of the image, like curves or edges of objects, as opposed to like?
We will get to that later. That's actually very interesting. Segmented backgrounds. This is very interesting. So this is a problem that also Lego does run into with their mosaic maker. I don't know what algorithm they use, but I think it's slower than mine because mine runs in less than. Sorry, Lego people. Okay. So if you have a massive background, like for example, Lego logo, this is from the Andy Warhol Marilyn Monroe set. And the best match for the background is like that pink color. But when you run the algorithm, it looks like a printer running out of ink, right? Like we literally physically do not have enough color to fill this in properly, right? We could detect it and manually process this, but this is very expensive. And it's like, even then you're like, oh crap, I don't have enough colors. What do? We use more math. We use something called pseudo dithering. This is a technique that I developed for Lego Art Remix. So we reuse our transparency color trick. The extra factor is like the extra factor, instead of accounting for transparency, literally just all it does is it encodes a little bit of information about the coordinates of the pixel. And it basically says if the sum of the row and the column is an odd number, I add one, else I add a little bit of extra distance, else I don't, right? And you can extend it to like different mod spaces. You can read into this a little more. It's a little difficult to explain like this if you don't have a background, but I know, take a picture of the slide. It's actually very, very simple. And the advantage of this, it's very scalable and it's incredibly fast. right? I actually, between making these slides and coming here, I came up with another alternating mod function for Lego Art Remix, which gets rid of like the diagonal banding pretty easily. Okay, 3D mosaics. This is another really cool thing. So input image, the hit 2005 album, It's Time by Michael Bublé. Who's heard this album? Right? It's got with hit songs such as Home and You Don't Know Me. Another summer day. Oh yeah. So what do we want to do? So instead of making just a black and white mosaic, wouldn't it be cool if we could raise some pixels above others, right? Because the whole point of Lego is we can build whatever and we can build in 3D, right? So what we want to do is we want to take an input image, and we, in addition to getting this stuff in the colors, we also want to get the depth information, and we basically need to say like, okay, maybe 2 or 3 extra layers. How do we do this? There's a concept of something called a depth map. Apple keeps on prattling on about it during their keynotes because they want to use it for portrait mode, but they should actually talk about this more because this is way cooler, right? At least I think so, right? So literally, a depth map is you have an image. For every pixel in the image, it has a value that talks about depth, usually 0 to 255. So what we do is we take the depth map, reduce the 256 different levels to like 2 to 5 levels, and we basically just create the depth image. What if you don't have a depth map? So if you don't have a depth map, there's actually a field of research called monocular depth estimation. A bunch of companies have actually put a lot of work into research around this. And there are many different models with different uses where you use a neural network that takes an input image. And if you don't have a depth map, it guesses the depth map. I mean, you could do it without a neural network. Most of the state-of-the-art approaches are neural network based. The one I use in production is one from Intel, which is really good. It's an open source one. That's pretty interesting if you're interested in that sort of stuff. Next up, we have backing plates. So in order to raise your pixels, you need to put something below it, right? So easiest thing to do is just get a bunch of 1x1s and put them in, but that's incredibly wasteful, expensive, and it's such a pain to remove them. Also, best to avoid like, what do you call it? Backing plates. Best to avoid large plates because they're difficult to remove. Turns out we can also use a different algorithm to fix this. This is the efficient tiling algorithm. And efficient tiling is basically built around the idea of we want to minimize the amount of plates used. And it's really easy to do this using the stones plus sand method, where you sort by the size and your algorithm basically puts in the biggest plates first and then tries to fill in the gaps. And as long as the lemma is, as long as you have access to 1x1 plates, it's guaranteed that you're able to actually fill in any input. And also, it's also guaranteed. There's another one where you like guarantee that you don't have to merge stuff. It's not optimal. There are some edge cases where this approach actually doesn't give you the best plate count, but in most cases, it's extremely good. Even when it's not good, it gets a solution. And more importantly, it's incredibly fast in practice. Okay. Pixelization. This is going to be the last section. Okay, I'll go through this a little quickly. Pixelization. The term pixelation is when we take an image and we like cut it down to a certain size. Pixelation is, the procedure that actually takes place in order to reduce the size. And the pixelization is deliberate pixelation. Now, what does that mean? How do I put this? I didn't think of how I was going to explain this. So when we actually reduce the image for the purposes of Lego art, we want to preserve the details in a way that makes sense in the context of Lego art. So that's what's called pixelization, right? It's used for pixel art in games and stuff and such. It's almost always done manually, but the whole point of this is we don't want to do it manually. And it's not meant for low resolution displays. It's meant for being seen upfront. Image retargeting is something we might speak a little bit about later. That's a separate thing. It's similar, but not quite the same. For example, we have the hit 2012 album by Taylor Swift, Red, which has songs such as, I think there's a song called Red on it, right? And the problem with this is if you run it through regular pixelation, this picture is very, very difficult to deal with because you see the edges over there, right? The edges tend to get blurred out through most regular pixelation, right? Because what does regular pixelation use? It does some smoothing. Every pixel is like the average of its surrounding pixels. But if you're on the edge, that looks weird. And when you get to Lego art, if you look really closely, like you can see that we've kind of messed up that photo, right? So there are a bunch of ways to deal with this. I'll kind of skim it. One way is to do voting majority, where you basically say, okay, if like, let's say like 75%, like pass like 40% of a area. So originally, let's say you have like a 50 by 50 area in the original picture that maps to just one pixel in the new picture, right? Now you need to choose what color I want, right? One way to do this is say, okay, more than 40% of the studs are red. Okay, screw it. I'm not going to take the average. Red, you win. It's really sad, but like that the other pixels don't get to express themselves, but voting majority can work really well. You can also use a superpixel based approach. This was a fairly recent paper. Actually, no, it's 2012. Interesting. But there's a paper about this where it basically from the ground up builds a pixelated image. They use it for like, pixel art and stuff, but it's once again applicable to Lego mosaics. Downside is it's expensive. And the final thing is seam carving. This is really cool. You could give a whole separate lecture about seam carving itself. We actually did this during in college during one class as a project. But it's basically like, hey, choose the interesting parts of the image and try to preserve them. This is really cool as a pre-processing step to try to cut down on the sizes of your backgrounds if you run into the image into the segmented backgrounds problem that I described earlier. I'm not going to go into too much detail, but look it up. It's really cool. Downside, once again, like the last one and like maybe this one, it's expensive, right? Like like I have a GPU accelerated version, but it's like it's really expensive to run from a performance perspective. Okay, so that's more or less it. I guess we have some time for questions. Before we actually get into questions, I need to plug my crap. I say plug, but it's not really a plug because all of this code here is free and open source. I don't make money for it from it, which is, I guess, it's not feasible to make money from something like this. But Lego Art Remix, you can grab the code on GitHub. Some of the earlier techniques that I described are really, really cool. Like I think like if, I don't know, we talk about Lego and STEM education a lot, but asking children to think about these sort of questions and try to make their own mosaic software, at least the basics, is like really cool. And if you only care about just using the app and you don't care about actually building your own, you can see a deployed version as well. It's free, it's open source, it's secure. Like future of this space, I think we should really move towards open source tools because like now that we have all this knowledge, now that we know how to solve the remix problem well, and now that we have access to very, very powerful client-side compute, in the future of this space, we should solve this problem in an open source way. I don't have every technique that I described in Lego Art Remix, mainly the more expensive ones. But if you really, really need a feature added to the tool, you can open an issue on GitHub or get in touch with me. No guarantees that I'll actually do it, but you can dig around the code, you can take a look at it, and like, yeah, feel free to use it for like whatever. Yeah, I guess that's it. Any questions?
Also, for anybody at home, are there any other questions from the live audience?
Can you describe what's happening with the seam carving?
Oh yeah. So this is pretty complicated. It's a technique it actually won like a bunch of awards.
What's different about the
So look at the first picture, right? The first picture is taken at a mall. There are better examples. It's just that this was the example from the actual paper author's website, where there's like the shop thingy in the middle, right? If you scale down the image, it shrinks basically when you're changing the size and scaling down the image. One way to do it is you can shrink the image, like you can like shrink it and then the proportions get distorted. You can crop the image which cuts off the end. And then there's seam carving, which attempts to remove the less interesting parts of the image. There's like this really crazy example online where somebody has I think it's a Windows XP background or something, and they cut it down and basically the algorithm only removes the sky because the sky is super quote unquote interesting.
Okay. Yeah.
And there are many different metrics to define what's interesting.
Can you please repeat questions from the audience
So,
for the benefit of those of us
question.
online?
Does the software have the option to mix round and square pixels?
Okay, so I don't think so. It doesn't have the option, but it would be pretty easy to code, right? Like what you would do is based on what was it's interesting, right? Because based on what position you are, you would either predefine if you had square pixels versus round pixels, and then based on that, you adjust your color distance function. Or whenever you're choosing a pixel, you consider both the round and the square version based on the brightness adjustment you do earlier. So I mean, it's feasible. It's just, I guess it's just like a paint to code from a UI perspective.
It might also be useful from a price perspective.
Yeah, it might be useful from a price perspective, but I think then you get into the question of, is the price difference worth it, right? Because we have an easy way to quantify through math if the price difference is worth it for different colors, right? We don't have an easy way to quantify through math. At least, I guess we could come up with one where if square really that much worse looking than circle.
We have some questions here in the chat as well. I don't know if they can hear us.
Oh, that's interesting. I hadn't thought of that. I know that's really worth thinking about, right? Because then you're combining the depth. So you combine the depth map approach with the normal approach. I hadn't thought of that. I'll have to think about that. Yeah. So you could use transparency, right? Because then what you do is you take the Lego, you take the pixel, and then basically you'd have like some sort of linear combination between like the transparency color and the regular yellow color. Okay, that's interesting. I hadn't thought of that. I guess you could do that. Somebody else had a question back there? Okay.
I don't know if you guys can hear us. Hello?
Yeah, so
Deb, can you also repeat the question for the
people? So he asked what languages and IDEs I use for this. I prototyped everything in Python because I'm usually do Python for like data science and stuff. But when I deployed it, I rewrote everything in JavaScript. The whole app runs in JavaScript. It has optimizations that allow it to run on the client. It's hilariously cheap to host this way. It can run on a phone this way. And I think Lego Art Remix I think it's got like what, 200,000 images to date. And so far it's cost me like less than $20 to host, which is kind of cool. So like efficient algorithm optimizations make things much cheaper and also much more secure. Like you can turn on airplane mode, it might still work. Yeah. Other questions?
There was one other question about can the algorithm also take into consideration a side of brick which is not a square?
Yes. Okay. This is really interesting. I forgot to say this. So if you take adjacent colors which turn out to be the same color, you can merge them. And this being just a backing plate, imagine this is a region of red. You can use the efficient tiling algorithm to fill it in. So yeah, the algorithm can do that. I don't think Lego Art Remix does that. I might code it in, but like it's a pain to code. That's most of the reasons why I haven't implemented this stuff. But like, yes, you can use this exact algorithm, drag and drop it in to merge the region together or merge adjacent pixels, whatever.
Another question was, are there algorithms for mosaics that can replicate the Andy Warhol style, the blockiness versus the dithering?
Oh, the blockiness instead of the dithering. So that's interesting. That gets into another concept called neural style transfer. You can read papers about that. It's a very expensive technique because it's a neural network based technique. But look up neural style transfer. It's really cool. Code is open source for that. So what you would do is, initially I actually looked into this, but it didn't work well with the constraints. So what you do is you run the neural style transfer as a pre-processing step to make your blockified image. And then after that, you apply like WART remix. It should probably work well. Yeah. Anything else? What's the time?
I just like to say, Lego Art Remix is wonderful. It's
Yeah.
really great. I've played with it and it's very fun.
Yeah, thank you.
It does a great job.
Yeah, it's free. Woo.
Thank you.
All right, that's all the questions from home. Thank you, Deb.
Yeah, thanks. Yeah.
Excellent.
Yeah, thanks. If anybody has any more questions or needs anything, you can contact me, I guess.
All right.
Yeah.